Thank you, Clay. Well, welcome, everyone. I'm sure you've seen the title. We're going to look at possible additional productive potential in existing fields. And the reason that we're focusing on existing fields is really just about the value of adding resources. Everything that you see will apply to exploration just as equally. So just a bit about me. I have 40 years of experience. I started with Gulf, and Chevron bought Gulf, went to work for them, Marathon and BP. So sort of a gimmicky thing, but it's fun. Since I started in February of 1979, this is actually my 6th decade in the industry. I didn't start when I was 4 years old. I've been a geologist, an engineer, petrophysicist, and a manager. I spent about half of my career in production organizations and about half in technology organizations. I was trying to figure out what a good image would be to apply to experienced trainer and mentoring. And since we're doing so much virtually, that is the reason for the on-air sign. So that is what I do. I have done it for quite a long time with former employers and now with PetroSkills. Something I have skills in and really enjoy is whether it's team or individual mentoring. I began training with PetroSkills in 2019, and I delivered 2 courses, Shaly Sand Petrophysics, which the materials you will see today are from that particular course, and then Petrophysics of Unconventional Resources or Unconventional Reservoirs, which we won't cover today. Okay, so we have an agenda. We'll look at a few log examples. We'll highlight some of the common causes of underestimating reservoir volumes. We'll introduce a few helpful tools. We'll have a summary at the end of the presentation, and then we'll open it up for questions and answers or discussion. What you'll notice on slides is I'm not a big fan just boring words and white space. I really like to have images. And these 2 images provide multiple purposes. One, they're an introduction to what this is all about, and they do provide really the crux of the information. And that is that in these 2 images, the one on the left is, do I have my laser pointer? Yes. This is an SEM image. The P stands for the pore, and the PT stands for the pore throat. And what we see is a fibrous illite that is going to destroy most of the permeability in that rock, and particularly when we coat all these surfaces with water and try and flow hydrocarbons, the effective permeability to hydrocarbons will be negligible. So that is when clay is bad. A similar volume can actually be good in the case of clay coats on these grains that may inhibit further cement precipitation, further growth into the pore space, and actually preserve permeability. So in this case, this rock has only 13% porosity, which is good for a lot of people, maybe not so good for others, but the permeability is great for everyone, 154 millidarcy. So what we'll talk about is the volume of clay is only part of the answer. Where the clay lies, its morphology, its distribution is more important probably than the volume. And the main takeaway is that if you take nothing else from this today, look at your pore systems. That's really the most important message. If you don't do it routinely, please do it. For any interpretation of complex pore systems, it's really critical. Okay. So are these reservoirs important? I thought this was kind of interesting. I looked in OnePetro, and if you look up shaly sands, which we will talk primarily about, although we have a carbonate example, you'll find almost 5,000 papers, the oldest being 1887, and just last year there were 164 papers. So not only is it old and popular, but it is current, right? In complex pore, if you look up that search, you'll find 26,000 papers. So every aspect of these reservoir types, the measurements associated, you'll find in one form or another, but there are some basic concepts, and we'll try and get those across today. So I'm going to show you some log examples, and most of the log examples will have a question. The question is not something that you need to answer in the chat or something like that. It's really a question to ask yourself, and then you'll get the answers following the questions. Okay, so let's look at this particular log. This is a log of the Smackover Formation in East Texas. If you look in the first track, you'll see an SP, and you'll see some good negative deflection across the interval. If we look at the resistivity track, we'll see that the deep induction resistivity is a solid black, medium, and SFL. So we have an invasion profile, and what we see is the shallows being most resistive. What we know from the SP, just as if for those of you, many of you may know about SPs, but some of the younger people, I shouldn't say younger, many of the people who've only dealt with oil-based mud may not have seen an SP. And this SP tells us, for example, the well was drilled with water-based mud, and the mud filtrate has a lower salinity or is more resistive than the formation water. And this invasion profile shows increasing resistivity with decreasing volume of investigation into the formation. Okay. So the question is this a wet zone? And I'll give you a hint. This is the one clean carbonate example that we're going to look at. So given this information, we always need to check scales. Deep resistivity, deep induction resistivity is around 1 ohmmeter. Is this wet? No. This well was completed and produced at 600 million cubic feet of gas per day with 600 barrels of condensate and no water. The reason that the resistivity is low is because there is an immobile brine, high immobile brine saturation caused by a continuous microporosity. Sorry, decline that. This sort of appearance is reasonably common when we have productive reservoirs in which we have contrasting big pores and little pores, and both are connected. So we have a conductive pathway through the brine associated with the microporosity and a conductive system that is not conductive in terms of resistivity, but conductive in terms of fluid production in the larger pores. Okay, so what about this one? This is the Frio Formation. This is a sandstone, bit lower permeability typically in South Texas. In this log, we see a clean SP. Again, it's a negative deflection. We see a deep induction resistivity near the depth track. There is a lateral log also available. The question here is this a wet zone? The entire interval here was perforated and made 3 million cubic feet of gas per day with no water. So the other thing I should point out before we leave this slide is always check your scales. This is a linear scale from 0 to 10 ohmmeters. So always be sure you understand physics of the measurements and the scales of the presentation. Okay, so why did we see that log response for this Frio sandstone? The grains in this reservoir are coated with smectite, and that's what this honeycomb is. It is a clay mineral. It is a swelling clay mineral. It has a large surface area, as you can see. All these blades in this honeycomb, that's a tremendous surface area, much of which would retain a brine coating, so there'd be a high water saturation associated with that porosity. And smectite has the highest CEC of the clay minerals. So all of these things will contribute to a lower resistivity. And to identify this clay mineral with some certainty, it would require X-ray diffraction. Okay, so in this particular example, this is a well, discovery well, drilled at the top of a structure And there was just a routine log analysis performed on this particular log suite. In this one, before we talk about the question, let's just look at what logs we have. In the first track, we see, again, a negative SP. So the formation water is more saline, more conductive than the filtrate. We have a gamma ray, and we see at the very top, this lobe that is the cleanest. It is the lowest gamma ray and most negative SP deflection, let's say it that way, which we normally interpret as clean. It has the lowest resistivity, and again, the deep induction is less than the medium, which is less than the SFL. And there's a porosity interpretation in which this is the highest porosity anywhere within the sandstone interval. And then something happens. We have this dashed line that separates this lower resistivity interval from a higher resistivity interval. We do see that the gamma ray and the SP, gamma ray is higher, SP has less deflection than it does in the upper lobe, and the porosity is diminished from the upper lobe. So could this dashed line actually represent a thin shale layer? Is this upper lobe really water saturated? And when I say wet, I don't know if I was clear on this before, but wet, and the way I usually mean it, is 100% water saturated. But many of you work in areas in which there are residual hydrocarbon saturations, but the water is the only mobile or productive phase. So if we just say that wet in this, for the simplicity of this presentation, wet means 100% water productive. So would this, if we perforated this top interval, would we make 100% water? That is the question. Okay, let's go to the next slide. Oh, sorry, one other thing to point out on this slide. So there is a labeled curve. This porosity is labeled as effective. We'll mention it again in a few slides, but this is one of the practices, calculating effective porosity using a bulk density to get a bulk porosity, and then subtracting some function of clay volume, is one of the reasons that we underestimate resources in our fields. I'll explain a bit more why in just a moment. Okay, so a second well was drilled because we had a discovery well. The bottom part of that reservoir was pretty certainly gas, hydrocarbon. We don't have a density neutron available to see if we see any sort of gas effects. The second well was drilled 150 feet down dip, and you can see a lower resistivity section at the very base. You can see once again the cleanest gamma ray, the maximum negative SP deflection. You can see again a resistive profile and the highest porosity. So is this the water leg? Is this the aquifer to our field? Is this slope the transition zone? And then we get into this resistivity that is relatively constant for a few tens of feet, which resulted in the calculation of a constant bulk volume of water. We often associate that, and if we have a single rock type that's often associated with a irreducible, let's call it irreducible water saturation, it would represent in a single rock type an immobile water saturation, whereas towards the bottom we see an increase in bulk volume of water, and we see this resistivity. We did get a bit extra information in this particular well. We have SEM images from 2 percussion sidewall cores. Just a word about percussion sidewall cores. Many of you may not have very much experience with those, but when I first started, they were common in just about every well because they were fairly inexpensive, and it was a chance to get a direct sample of the reservoir rock. In this particular case, what we see is the SEM of the percussion sidewall taken towards the top of the reservoir has a lot of cements, a lot of overgrowth. You can see these faces as we grow the cements on the grains, whereas this sample, from as we see the porosity increasing, has a clay coating on the grains, and you see the pore reasonably well preserved. Well, in this particular case, we actually have dynamic results because both of those wells were hydraulically stimulated and flow tested. And the up-dip well, number 1, had no mobile water, had an initial rate of 7.5 million cubic feet of gas per day. And well number 2, no mobile water, so we may expect gas further down dip. And the initial rate was 9.5 million cubic feet per day. So why are there clean, low resistivity intervals? What is that all about if it's not fully water saturated and not water productive? What's happening? So what we saw in the SEM of the percussion sidewall core was that we have chlorite, and this blady habit, this blady appearance is often associated with chlorite, and that inhibited further quartz overgrowth and provided a high microporosity and water saturation, but the water is not mobile. The upper part that had the cements had further cement occurrence because there was not a chlorite coating on the grains to inhibit that cement growth. So why was it clean? Well, the chlorite has no potassium, right? So it's going to contribute little or no gamma ray. It's usually there's a solid substitution series. We'll see magnesium and iron typically in these clay minerals. But in essence, this is the good clay situation in which the clay protected our pore space, and where we didn't have the clay coatings, we lost porosity, and so the reservoir was more resistive where we had the more cement. And the last point, sorry about the laser pointer running around. The last point was that we overestimated water saturation in the low resistivity zones by using the same Archie parameters in the cemented and the uncemented. So with less cement overgrowth, less quartz overgrowths, we would see an M of 1.6, and in the more cemented intervals, a 2.03. So if we assumed, as we often do with the lack of information, that M would be equal to 2, we're not too far off in the cemented region, but we overestimated the formation factor in the less cemented or the clay-coated region. Excuse me. And we see a similar effect with N in the clay coats because we have a continuous microporosity filled with conductive brine. The N then is only 1.72, and in the more cemented section, it's 2.07. So again, if we assumed M and N of 2, we're not too far in cemented, but we greatly overestimated the volume of water in the clay-coated section. And we may compute a water saturation of 50 or 60%. However, in this, where we have these clay coats, 40 to 45% of that water would be immobile and reside in the microporosity. So we overcalculated the water saturation, and most of the water saturation that existed is actually tied up in microporosity and not mobile, and that's why we didn't cut any water on completion. Okay, so this, I started my career working Miocene reservoirs on the Louisiana state waters coastal shelf, and this was a fairly common looking example. You may hear terms low contrast, low resistivity. This is a low contrast pay, and if you just look at the resistivity track, where we have a deep induction and an SFL, you see very little, you see some little bumps, but nothing. If all you had was that resistivity track, you don't see anything that might flag a reservoir. If we go back over to the SP and the gamma ray, we see that there is a shale section, and then we get a deflection that indicates that there is some sand in the section, but we get no similar deflection over here on the resistivity. So this cartoon of circles in a rectangular box represents perforations. So the question that normally goes along with this, particularly if we did animations and didn't give you the first track, you got the resistivity and the perfs, and the question would be, well, is there any sand? And with no more information than just the resistivity, you'd have to say you don't see anything that looks different than through the whole section. But when you have the gamma ray, the red dashed gamma ray, now you know that there is something that is less radioactive in the interval with the perforations, and you have an SP, and because it is deflecting, and it is deflecting negatively, we know that formation water is more conductive than the filtrate. We know that there's permeability. So now we know that there is some sand, there is some permeability. The main question being, can this interval produce hydrocarbons? Well, yes, this exact well did produce over the course of 18 months 329,000 stock tank barrels of oil and 4.5 thousand barrels of water, which is about a 1.4% water cut. So there is some water associated with the production, but it is a very minor cut, and I don't know what fraction of that might have been completion fluids. This was a fairly common example. There was a book, let's call it, the form I had was a 3-ring binder with a bunch of examples. But if you were to look back, the New Orleans Geological Society and the Houston Geological Society put out essentially a catalog of these sorts of examples in 1993. It was called Productive Low Resistivity Well Logs for the Offshore Gulf of Mexico, and it was just pages of examples that look like this with some production information. It was this whole thing about these underexploited resources goes in waves. In the 90s, this was a very hot topic, and it appears about every 10 years. So it is time for the cycle to heat up again to find these resources that exist in our fields. So anyway, I just wanted to let you know about that particular resource. It's still available from a few places. Okay, so let's talk, I mentioned about effective porosity. So what else can cause us to under-recognize? Many times we'll have shows in the well, so it's not as though we don't know there are hydrocarbons, but oftentimes we think they may be residual or not economically important or whatever, and that's why a lot of these reservoirs, maybe they're tested once or twice, and we'll see here on this slide as we go through it, why you can have negative outcomes, and that oftentimes causes people not to want to try these completions again after being burned a couple of times. Okay, so let's get into the meat of the slide. Sorry about the laser pointer again. So the limitation that likely most often inhibits full recognition is we're going to do a resistivity-based evaluation. By routine, meaning that we take it as just a bulk interval. We don't think about thin beds below resolution of our logging tools. And then we use some net pay cutoffs, which in many places, they're almost a matter of habit rather than tailored to the specific reservoir. So if we, I just got a loud beep. Hope I'm still connected. If we use the cutoffs that we typically use on massive reservoirs, on thinly bedded reservoirs, for example, or shaly sands, we are going to have a problem in evaluation. We're going to underestimate our resources. We may not all agree on what cutoff value should be, but we can all agree on what the definition of cutoffs is, and that definition is they are thresholds, one or more thresholds applied to log calculated properties, because we want to identify those intervals that bear hydrocarbons, have little to no mobile water, and have economically significant permeabilities, right? That is the reason cutoffs are applied to logs. Okay, so if we apply, and we all do, and it's the most common first pass evaluation applied to logs is we go through and we calculate a total porosity from our bulk density, we calculate a bulk Archie water saturation, and then we apply some cutoffs and we generate some flags to see what we're going to look at more carefully. A V shale cutoff, which is common, in a laminated interval actually represents the complement of net to gross. So the 1 minus V shale really is the sand volume, and if we have a shale cutoff, say for example 50%, then we will limit our sand volume and occasionally miss complete reservoirs. The same is also true that we will have shales in what we're calling all net, but the point that we really want to make here is that we are going to underestimate the length of our reservoir because of the cutoffs. We'll lose some net thickness, and occasionally, an example in this core UV ultraviolet light photograph, where the fluorescence represents oil, we would not have that would not have been a reservoir that would have zero net at a 50% V shale cutoff. Okay, the other problem that we have is all these black layers are shales, and they're going to be conductive, and they are parallel to these sand beds. It's all nicely layered, and those would provide conductive parallel layers and strongly reduce an induction resistivity. And that's the main justification for the triaxial measurements, triaxial induction measurements that are popular. If we had clays in these sand layers, they can further reduce resistivity, and that's why we have a Waxman-Smith model to account for those extra conductivities beyond the brine. But that may still pass the porosity cutoff. And we saw initially that some of those very fibrous or wispy clays may pass, it doesn't take a large volume, may pass a porosity cutoff and not pass a permeability cutoff. Okay, and then there is water-filled microporosity, and that will increase the water saturation, which may fail SW cutoff, and we saw a few examples of that, and yet the reservoir does not produce water. So this is the example that I just mentioned with the fibrous stuff, that if we have clays blocking pore throats, all the cutoffs may be passed, we have low productivity. So the key, and this again is your takeaway, understand your pore system. That is, if you take only one message, that is the one to take away. Okay, so let's talk a little bit more about this and why V shale is not enough information in really in just about any circumstance, right? It's one of the more common things calculated by people, but is one of the more misleading and has caused a lot of bad decisions. And let's see why. So we have three images here, and there are three classes of shale distribution. Most reservoirs, real reservoirs, have some mixture of these. It's rare that we have, other than laminar shale, we do see that quite a bit on its own. But you can have shale rip-ups occurring in most environments, and you can have a dispersed shale in many environments as well. So let's look at the effects of having this laminated sequence. So what we would have is a sand, these yellow grains, in which we placed a shale layer. And to place that shale layer, what we had to do is we had to take out some volume of sand as a layer and insert this shale layer. Doing so has a number of impacts. One, as we mentioned in that previous slide, the shale would be parallel. If our borehole was drilled normal to bedding, then we would have parallel conductors, and it would drop the resistivity based on induction resistivity substantially. It will also reduce the bulk porosity because we're replacing, say, for example, a 30% porosity sand by some layer of, say, 10% porosity shale. So overall, the bulk porosity is going to vary as a function of how many shale layers or what the volume of those shale layers are in the interval. And maybe the most important part of this for laminated stuff is that the shale thickness, so a V shale or a net to gross really reduces the permeability thickness product only by thickness. In this particular case, we have retained the permeability of the sand, and so we can have a quite productive system because of the sand permeability. We just lost the thickness of the system. Okay, so that's a very key part of this whole process. In the case of a structural shale, what we've done is we replaced a sand grain that has no porosity with a shale grain that has, as we made the example, 10% porosity. So what happens is the resistivity doesn't really change because we're just substituting one solid particle for another. We do increase the bulk porosity because whatever volume of shale we have at 10% is replacing sand grains at 0% porosity, so it raises the porosity of the bulk. And there's no change in permeability. So although we have shale, the permeability is what we would expect for a clean sand. There's a little disclaimer here, and this is assuming typical small volumes of these shale grains, because if we have a lot of those, they will deform and they will extrude into the pore space. And if you have a lot, it is detrimental to your permeability. But the typical, what we'll see in scattered rip-ups and those sorts of things, don't really cause much of an issue for permeability. This is the one to discriminate, the dispersed shale class. In this one, the bulk resistivity depends on the clay type and morphology, because we can have this extra conductivity. We have cation exchange capacity associated with these clays, and we can have an additional source of conductivity depending on the clay type and how it is, its geometry within the pore space. We will reduce bulk porosity because we have taken 100% porosity fluid and replaced it by some volume of clay. And I'm making a distinction here between clay and shale. Shale, and this is an important distinction, but we won't dwell on it. Shale being a lithology that has clay minerals, but also has silts, can have organics, a number of other things. So it is a lithology, whereas clay in this sense, clay is really a grain size, but we mean clay minerals here, these phyllosilicates, and that's a distinction. So if this is an orthogenic clay, it would be 100% clay, and if it is a detrital shale, it will have clay, but it could have other materials associated with it. In any case, if we are filling the pore space, and particularly in the pore throats, small amount of clay can, as we saw in an image, can severely reduce the permeability. Okay? So, I've given you a problem, and now let me give you some solutions or some aids that can help you to reduce your uncertainty. One of these is geologic information. So if we recognize depositional environments that are prone to thin beds, then we know to expect them. And if we understand the depositional environments, we may know something about aerial connectivity, which is very important to make these completion decisions, or aerial extent and connectivity, let's say. Then we also have the opportunity to characterize these post-depositional processes, which would be likely to form orthogenic clays and or other cements. So we know something about age and temperature and pressures. And so there are some predictive tools from the geologic side that are extremely important to evaluate these types of reservoirs. Mud logs are also extremely critical information because we have direct hydrocarbon indications. We get shows, we get gas easy for me to say, chromatographic information that might help us to understand something about the hydrocarbon type, and so on. The actual sample descriptions, nowadays with modern bits, they're usually inadequate to help us for something this fine scale to start with, and the sampling is generally too sparse, even at 10-foot samples. It's not going to be that helpful. Okay, but the shows are that is the indication that we need to go and look more closely. Okay, so we have petrophysical models. We have things that help us work out shale volumes and distribution, that discrimination we said we wanted to do on the previous slide. And we have models that help us to understand and account for excess or extra is the right term, conductivity in these shaly sands. There are some logging measurements that can help us as well. Triaxial resistivity, as we said, the parallel conductor problem. Borehole imaging helps us a bit with the net to gross. And nuclear magnetic resonance can help us a lot in partitioning pores and where and which pore types and sizes water saturation may reside. And then if we are fortunate enough to have some core material, there are lab-based techniques that we should employ to detect and quantify this extra conductivity. Okay, so as an example of the geological information, we see a log, we see that it is layered, and it's fairly close to the resolution of the resistivity log. We see an expression on the gamma ray. We see an interpretation of environment. In this particular case, we're looking at a turbidite. Turbidites often, particularly on the fringes, will have some thin beds, and that's what we see in a white light core photograph and an ultraviolet light core photograph. The gray is the shale, or in this case, the black and the ultraviolet is the shale. The sand here is actually a lighter gray. You can see some invasion, and the darker parts are due to oil staining, and so the whole thing fluoresces. This sort of resistivity profile is also common. I just want to point that out. So we have it's called RT and RXO. Could be a deep induction and something shallower. So the shallower curves typically have a higher resolution, and the resistivity in a lot of these thin bed intervals will be the greatest on whatever has the best vertical resolution and the lowest with the lowest resolution. So this is a resolution effect. Okay, so on a petrophysical tool, we have something that this Thomas Steiber model that was published in 1975. And it's actually a very logical model, and it's very helpful to think in these terms as well as a tool to apply to your data. So let's just walk through the concept very quickly. So we have a point that is a clean 100% sand point in porosity and sand point in gamma ray response. We go to the other extreme, we have a shale porosity and a gamma ray of shale. This third point can be calculated because it represents the dispersed endpoint. If the porosity of sand, so this is a gamma ray equation. So we have the gamma ray of sand and the porosity of sand, and we fill that sand porosity with this shale. So we have the gamma ray of this shale filling the porosity of the sand plus the gamma ray of the sand. So that's the gamma ray response. The porosity response, this minimum, is the porosity of the sand filled with the porosity of the shale. So all we would have to do is take this porosity of sand, that's the volume of shale, the porosity of the shale, and that will tell you how much porosity remains in this bulk interval. This is the minimum. So let's just look at a quick example to explain a bit more about this effective porosity that we talked about. I also want to point out that a structural shale will go in this way, in which the porosity is increasing and the gamma ray is increasing at the same time. That would be an indicator of structural shale. Okay, so in this particular case, we're saying that the gamma ray of sand is 10 and the porosity of sand is 30. 110 for the gamma ray of shale, 10% porosity for shale, and we put in a point. The point lies on this line, which is simply the thickness weighted average between the sand and the shale. That's what laminated is. We take out some section of sand, put in a section of shale, and then you go up and down this line. So if you land on this line that connects these 2 points, you have a laminated system. So already we discriminated it from other forms. And what you'll see is this has a gamma ray index of 0.5, has a net to gross of 50%, and it has more higher gamma ray, more shale, than the point at which the pore space is completely filled with clay. So this is a very important distinction. Higher shale here is actually better than the lower shale here, right? Okay, so the other thing to observe is that the bulk porosity at this point is 20%, 50% mix of 30 and 10. That would be the porosity we would calculate in this interval from a density log with the proper inputs for matrix and fluid. Unfortunately, we've already underestimated the porosity of the sand when it comes to productivity. So far we haven't really destroyed anything on volume because this is the calculated average volume of the whole thing, but we have underestimated the resource for hydrocarbons because the sand porosity is actually this 30%. It's just interlayered with 50% of this shale. And then if we took and calculated an effective porosity and subtracted some function of shale volume to account for the shale porosity from our 20% bulk, we would likely end up with a non-reservoir, in which case we actually had remaining 1/2 of the KH of the clean sand, the porosity of the clean sand, the water saturation of the clean sand. We just lost that 50% volume, so this may still be a productive reservoir. Most of our treatments of these kinds of rocks would render it to be considered non or marginally productive. And so this is one of the reasons we miss out on these types of reservoirs. So this is why B shale is not enough. Knowing where you are in this axis tells me nothing about where I am as far as where the clays reside and how they impact productivity and volumes. And we also see that effective porosity, if we did it right, we may not lose hydrocarbon volume, but we will grossly underestimate the production potential of this section. Okay, so in this image, we see these different forms of very fragile clay textures. We see little fibers, we see little plates and wispy things. So just it's a question, but it's really a point to you is, does your core program, if you were going to core some reservoir such as these shaly sands, and you might have some of these structures, does every part of your process from cutting the core through lab processing analyses, does it really preserve these structures? Are you really characterizing the pore space unaltered, or are you characterizing an altered pore space? So if you do believe you have these delicate clays, you really have to set up your entire program to deal with them so that you represent this pore system and not something in which all these clays are flattened down against the sides of the grains or otherwise affected. Okay, so on the conductivity model, what we have is, we'll look at Archie. Everyone knows Archie. So Archie simply says that the conductivity of a wet rock, C sub 0, is proportional to conductivity of the water in that rock. And this constant of proportionality is this formation factor. Because we're in conductivity, it's 1 over the formation factor. If it's in resistivity, this is the form you all know. The resistivity of a wet sand is equal to the formation factor times the resistivity of the water in that sand. And it's this nice linear thing. We get the slope of F, or in this case 1 over F because of conductivity. If we have this extra conductivity provided by, so in Archie, all the conductivity is provided by the brine. In the shaly sands, we may have conductivity provided along the solids, and that is what this is. So it's framed in the same way as Archie. The conductivity of the water-saturated rock is 1 over F, but it's F star, which is corrected for shale conductivity, and it's conductivity of water, but there's this extra term. Right? That's what this extra conductivity is, and this is Waxman-Smith's. And in the laboratory, you can run this experiment, and it's commonly called a COCW measurement, in which we look for this extra conductivity in these shaly sands. And that's all we'll say about that, just to make you aware that it exists. I also want to make you aware that these shale laminations can impact things that we normally consider massive sands. In the first track, we have a gamma ray, green curve, a net to gross calculation, and in this, the V shale is less than 10%, so the net to gross is over 90%, and this is a 25-foot thick sand, and we don't see a bunch of wiggle and noise on the gamma ray, so we might think this is a massive sand. One of the things that is becoming more common nowadays is modeling resistivity, and this is there to explain what really happens. So in this particular case, we're looking at the highest, shortest spacing, highest frequency, highest resolution log that we have. We're going to forward model that log through imposing a model, so sort of an inversion. The imposed constraint we're going to put on here is the resistivity calculated from a saturation height function based on rock types and a shale baseline. The green boxes, so this is a layered model, and you can see towards the top, you can see these are boxes. The little spikes to the left are boxes of shale, and the line, what looks like a line to the right is the box of sands, and it is meant to go along the resistivity calculated from the saturation height function and back to the shale baseline. Inversion is non-unique, but this is a model that is consistent with these imposed constraints. And what you see then is the formation is 3.5 times the highest resolution resistivity. If we look at, this is a curve commonly used as R deep, which is not true resistivity, but it is labeled R deep. And the formation resistivity is actually 6 times higher. So what does this really mean? Tell me about volume. So if we look at the assumptions we'll make here very quickly for these 3 cases, we'll use a water resistivity of 0.035 ohmmeters, M equals N equals 2. The bulk density over the interval, we'll just say we took a point and it is 0.27, 27% porosity. We calculate water saturation from Archie in all 3 cases. In the bulk model, we use the resistivity of 10 and that porosity, and we get a water saturation of 22%. Sounds really good. What's the problem? A massive sand with 22% water saturation sounds right. Well, if we use the laminated model and we model the resistivity, we end up with 35 ohmmeters in the sand. We didn't do anything yet about the density, so we'll use 27. We see water saturation goes from 22 to 12, so we increased our oil volume by 13%. If we also accounted for the shale porosity, the sand porosity goes up just 1 pu, but we end up with a water saturation of 11, but the combination ends up with an 18% increase in oil volume over the base case. So even in massive sands, shales can make a difference. And if you want to find out more about this, there's an SPE reference below. So to summarize quickly, sands and shales affect log responses in siliciclastics, even in what we normally consider massive. Thin-bedded sand and shale sequences, and for this purpose, thinly bedded means the layers are below log resolution. It's important to discriminate shale geometries, because in a laminated case, this thinly bedded case, as we said, the KH only declines with thickness. The permeability remains that of the clean sand. In a dispersed case, that's the other case that really, it's very important to discriminate between these two, because the dispersed clay, the authigenic clay case of dispersed shale, very little clay. You may have 100% thickness because you passed your cutoffs, but no permeability because the clay plugs your pore throats. It's very important to recognize those two things. Clay can be good, as we saw, and inhibit quartz overgrowth. It can retain or reduce Archie electrical properties. And what that means is we're not having more complex cementation. We're retaining the original pore geometries with these clay coats. There's usually a high microporosity associated with these clays that are typically 100% water-filled, and that can provide an additional continuous current path. The clays can provide an additional current path than that from formation water. In this image, once again, we're just seeing that a substantial part of the water saturation would be immobile and contained in microporosity. So there are other tools that, there are a number of tools. We introduced a few or showed a few to help with the determination of shale volumes. Even when more than one geometry exists within the same sedimentary sequence. There are models to understand shaly sands. We saw an example of how we would consider Weishman-Smits. There are others that help us understand partitioning of water and porosity and hydrocarbons by size and location. We didn't, in this presentation, talk about Hill, Shirley, Klein, but it is a key concept that goes along with shaly sand interpretation. V-shale from a gamma ray log can be more misleading than helpful, right? Because it didn't have enough information. We might try something that looked clean and be disappointed, or not try something in which we would be quite happy using V-shale alone. Cutoffs without customizing them to achieve your objectives, just using common porosity, V-shale, water saturation cutoffs is a key contributor to underassessment of resources. And effective porosity, by any other definition than the bulk volume of mobile fluid, shouldn't be used for the characterization of shaly sands. It will cause you a lot of problems. This little image shows you, and it'll be, we won't go through it now, it'll be in the recording. Many of you know this one already, and it just describes different pore spaces and where water resides and what logs are sensitive to which parts. Okay, so there are, if you're dealing with shaly sands, I highly recommend taking the shaly sand petrophysics course. There are a number of other courses that can help you. This little box is probably the most important part of this, that if you really want to provide a reliable description of any complex reservoir, we saw the first example was carbonates. Carbonates are complex, shaly sands are complex. You have to use all of the data, and there has to be integration of information and concepts to make maximum use of those data. And that is your other takeaway. Look at the pore space, use all the data. Those are the two most important takeaways that I can give you. And with that, we are at the point in which we can look at questions or discussion.
All right, thank you, Jeff. So I've got a couple questions that came in during the presentation. If others have questions, go ahead and type them into the chat or the Q&A now, and then we'll get to those. So first question here, Jeff, is which type of shale is most common in highly productive reservoirs? This one came in on your slide where you had the 3 different shale types.
Yes, so without going back, just very succinctly, the laminated, because we're losing thickness but not permeability. The structural shale would also preserve permeability, but it's not that common, and you won't get large volumes of structural shale. So really the most common cases will be dispersed and laminated by far, almost exclusively will be where the production is going to come from. The dispersed will be a negative outcome in most cases.
All right. Next question here is, why is it that shallower resistivity measurements have a greater resolution?
Okay, so I'll answer that, but I need to add one other caveat to what I said about the laminated. So in the case of older rocks where there's been a lot of temperature and pressure, and we have a lot of quartz overgrowth and things like that, dispersed clay is the case of coatings, grain coatings by clays, and so that will preserve permeability. We'll find places where chlorite is a really great preserver of porosity, so that is the one exception. As far as minimal diagenesis, is going to be laminated. If you have a lot of diagenesis in your reservoir, then clay coatings will be quite important. Okay, so on the resistivity, typically the depth of investigation and the spacing or vertical resolution are proportional. Normally, as you add resolution, you decrease depth of investigation, or if I want a deeper investigation, I lose resolution. For most tools, that's going to be a general rule of thumb. There are some exceptions with focusing and processing, but in general, that's how the tools are going to work.
All right. Next question says, and this is referencing slide 12, with just a GR and res SP, the interpretation suggests that there is a permeable sand and lower form water res, but high bulk SW. With no pore structure info, what influenced the perf decision?
No, that's actually an excellent question. So many of these reservoirs were found. The first bit of information you have that tells you there's something there is you would have had something on the mud log. Okay, you might have had to show increased gas response. In this particular time when these things were happening, percussion sidewall cores were quite common and relatively inexpensive, and you could go in and they came, they're pipes with bullets. They're cylinders, and you would fire, and you could shoot 90 of these things. And it is possible that you would be so unlucky that you missed all the sand and only got shale, but that's typically not the case. So that's the main way that most of these were found, or what would lead you to there would be these logs, percussion sidewall cores, mud log show.
Okay, and then next question says PHIE going forward, yes or no?
I would not use an effective porosity, nor would I recommend anyone use an effective porosity. There's a whole can of worms, and when we get into effective water saturations that go with that, we bring in even more chances for something to go wrong. So I think you're better off understanding total porosity and understanding your pore system and the distribution of shales.
Okay. This next question says, this is concerning the three first examples with the funny resistivity response on top or on bottom, where we would not expect any hydrocarbon production, but rather water.
Yeah.
It says, could you explain the reason for inverse invasion profile on resistivity response?
Okay. So this is one of the pair, right? So well, let's go to the other one because it's on top and it's maybe the only way we would really expect this to be water is if this dash line was a hydraulic barrier and truly isolated this section. Okay, so the resistivity profile, if this was really wet, a 100% water-filled interval, we would expect a profile to look just like this because the SP, remember, has a negative deflection, so the mud filtrate is more resistive than the formation water, so we would expect the shallowest curve to be the highest and then collapsing to the lowest resistivity. Now, the one question that wasn't asked on here, but it is an important question, is given this porosity, what, and the brine, the salinity of the formation water, what would we expect a wet resistivity, an R0, to look like? Could it be 0.7, or does it need to be 0.3? Do we know that this is already too resistive to be a wet zone? I don't know the answer to that, but that's one of the things that you would want to know in the interpretation of this. Now, the one thing that we know, there we go, this will work. All this surface area of all these grain coats by this chlorite, So this is all high salinity brine that's associated with all these surface areas. And so, excuse me, we have a very high water saturation, higher than what we'd have without the clays. We have, because of the surface area, we have a high water saturation. We also, if you recall, because we didn't have additional cements, we preserved the original pore system, and so our M's and N's were lower. So we've overcalculated water saturation. Most of the water that we have calculated that is truly there is tied up in the microporosity. And so this excess porosity, part of it is retention of the original pore system. A good part of this porosity is the microporosity associated with the clays. So the profile is that we've displaced some water in the near wellbore. So we can, so that is one of the things that can happen. We can bank water, and those of you who have seen, well, I won't go off on a tangent. We can displace some of the near formation water. We can displace the hydrocarbons, and we can have this RXO. We can have this more continuous high water saturation associated with these clays that's influencing deep. The other thing happens to do with the types of logs these are, right? The induction is going to be most focused on this conductive, continuous brine pathway. So all these are contributing to this profile and the lack of water production. I hope that answers the question. I know that was kind of rambling, but hopefully I got there.
All right, next question is, does the difference between epithermal porosity and thermal neutron porosity indicate clay presence?
Oh, that's a good one. So the difference, that's a really interesting question. It has to do with the thermal neutron absorbers, right? And so we typically see shales having more of that. Epithermal would be more related to porosity without these associated thermal absorbers. So does it necessarily indicate clay? It's most commonly associated with clay, but I don't think there could be other reasons. Does it really affect? Yeah. That's a good question. Normally, we do expect that the thermal absorbers are going to be associated with the clay zone. So, yeah, it's an indicator. It's not necessarily a direct quantitative answer, but it's an indicator that you would need to conduct an interpretation of that difference.
Okay, then a couple more here. What would be the order when it comes time to classify clay because of the radioactivity?
Right. So what we normally think of as a primary contributor to a gamma ray response is potassium, right? Some percentage of potassium is going to be radioactive. And we see that illite has potassium in its composition where the other clays don't. Fortunately for us, and the reason gamma ray has been used as a lithology indicator is the most common clay in most shales is illite. And because of the illite, we have the potassium, and so we get the gamma ray response. But if you were to, and I encourage you to do this, and this is something that we go into some detail in the class, but if you were to look up in any reference the chemical compositions of clay minerals, you'll find that you won't find potassium except in the illite. And so illite is #1 contributor to gamma ray, and the other ones, unless they have other things associated with them. But as far as the crystal, the clay itself, we don't find the potassium of any consequence that would give rise to a gamma ray response.
All right, and this is the last question, unless any come in through the chat, so kind of last chance. And whoever asked this question, is either genuinely curious or has a funny sense of humor. They ask, is there any relationship between guitars and petrophysics?
Yeah, absolutely. The more musically inclined you are, the more you like petrophysics. No, I don't know. It's a funny thing, but I do know a lot of petrophysicists who are into music, and I think the majority might even be into guitars. So it's a left brain, right brain thing, right? It just brings balance to your life.
Yeah, I'm sure there's some connection there with waves and frequencies and that sort of thing, I'm sure.
Right.
Resonance, so.
Yeah.
All right. Well, hey, thank you, Jeff, so much for the presentation and the Q&A. That was great.
Oh, thanks. It was my pleasure, and thank you all for attending and sticking with us through the questions.
Yeah, thanks, everyone. Make sure and check back. We'll be adding some new webinars over the next few weeks and try to keep doing these each Tuesday. So we hope you can join us for future sessions, and thanks for giving us some time today. Stay safe, everybody, and take care.
Bye, all.